de Hidalgo. Okay? And she's one of the youngest doctors that have graduated with the quantum. She will talk us about propagation of Hermite Gaussian modes in the parabolic media.
Thank you. Good afternoon. I am Zulema Gress, and I would like to thank the organizers to the invitation to be here and present my work. Today, I want to talk about the propagation phenomena of the electromagnetic modes. In particular, we start Hermite Gaussian modes, and this work is in collaboration with Sara, Icon, and Javier Negro. Well, let's start. I want to start describing the propagation phenomena for general electromagnetic modes. In this case, well, in parabolic media, but what means parabolic media? Parabolic media is an homogeneous medium with a quadratic refractive index profile, like in this way. So where R is related with the radial coordinate, alpha is a parameter related with the focusing of the medium. Later we will see what means focusing properties. And to describe the propagation phenomena, we use the paraxial equation. And for this medium, we use, well, the corresponding paraxial equation is in this way. So in this part is about the x and y coordinates related with the transversal behavior of the beam, and y is propagating along the zeta coordinate or optical axis. So in this case, U is a component of the electromagnetic field, and we are interested to find solution for this equation where the light have this form. Is to say, we are interested in light with behavior as a beam that it has a localized behavior, so that we are interested in solution of the Gaussian Wacket package type. So we propose the solution for this for the last equation. In this part we have the Gaussian behavior. So with the parameters W, R, and this letter is related with the behavior along the optical axis. So W is related with the beam width, and we can see it is in terms of the cos and sin. And R is related with the curvature radius of the wavefront of the beam, and we can see this parameter is in terms of this the other parameter, what is longitudinal. So, and this is called Boy phase, what is a phase for beams propagating. So, but we see we analyze that Gaussian beams works well to satisfy the equation of to satisfy the paraxial equation. But we are interested to find other solutions that more interesting. In this case, we propose again a new, other solution for the paraxial equation. But in this way, we have this part have the Gaussian behavior, because we still interested in beams localized, and we introduce this function f, which contains all the information about the transversal information of the beam. So also we can find that this function fulfills a equation of oscillator And taking advantage of this form, we propose the factorization of this function in this way, in terms of the label oscillator operator defined in this way. So, which this operator satisfies the Heisenberg algebra, and the action of onto the function f is in this way. So with this we can express the solution that we have proposed in this way, where this part are the Hermite modes, and in this part we have the Gaussian behavior. So for that, these modes are called Hermite Gaussian modes. So we can see these modes are labeled by two levels, N, I, M, who are related with the X and Y axis respectively. So in this slide I show some different Hermite Gaussian modes. In particular, for example, we can see the label N is related with the nodes or in the x-axis, and label M is related with the nodes in the y-axis. So we can see that this intensity distribution are lobes, bright lobes in a rectangular arrangement. So, for example, the last one, we have the Hermite Gaussian mode 1, 1, and that means that we have one node in the x-axis, and we have one node in the y-axis. So, we analyze the propagation of these modes in a parabolic medium, and we find they have this particular behavior. So where the properties of the focusing of the medium and the propagation, dispersion of the beam are combined. So in the first one we have a parameter, well, here I don't put the parameter, but alpha is the parameter who decides who will be the behavior. But in this case it's a normal Hermite Gaussian beam who propagating along the zeta axis. So we can see this tends to disperse like a normal beam, but in this case we combine the focusing properties and the dispersion properties. So the beam starts to disperse, but then with the property of focusing, they tend to autofocusing, self-focusing. And in this case, it's the same. The property of the focusing are more important or have more weight than the dispersion of the beam. So we can express the last Hermite Gaussian modes in terms of the later operator A and B in this way. And this form allows to introduce other operators, A and B capital letters, defined in this way, so that we can see in this part that the Hermite Gaussian beam are like a subsequent action of the operator A and B onto a fundamental mode, that in this case is the Gaussian mode. So this action, subsequent actions over this Gaussian mode, we can construct the Hermite Gaussian beams, where this operator A and B, well, big A and B satisfy this commutation relation, and so also they satisfy the action of the Hermite Gaussian beam are in this way. So a graphical representation of the action of this operator A and B capital letters is in this picture. We can see that operator A shift the N label, and the operator B shift the M label. So we can will be possible to construct or other operators who allows us to shift modes in this way, in diagonal way. Is possible? The answer is yes. We can construct other operator which are called L plus and L minus, and this is a combination of the operator A and B in this way. So operator L we can allow us to shift onto a specific hierarchy, and continue with that. We have the define this operator like a combination of the operator A and B, so that this operator satisfy this commutation relation, and to analyze the action of this operator of the Hermite Gaussian beam, we define a new label who is called L, and in terms of the NIM labels. So that is why here we can see the Hermite Gaussian beam NIM, well, labeled by NIM levels, and now is in terms of the new label L. So here we have the action of the operator L plus, L and L minus onto the Hermite Gaussian beams labeled by these labels. So, and we can find that this is the representation of the SU11 group. So, to analyze the propagation of the beam, we can use several tools, but in particular, we use to analyze the propagation of these modes. We use the coherent states, so that is why here we construct the coherent state for these modes. Since these operators satisfy the SU algebra, we construct the coherent states using the Baruch-Girardello approach, which is defined in this way. So the coherent state is defined in this way. So in this part only I want to show that they minimize this inequality, where this L1 and L2 are defined in terms of the L plus and L minus. So we graphically of these coherent states for different phases, and we have three examples here, and we can see the coherent states of these Hermite Gaussian modes have this kind of particular behavior. We can remember that the Hermite Gaussian beams are lobes, bright lobes in a rectangular arrangement, but the coherent states of these modes are like circles, ovals. So we can analyze the propagation of this mode in the parabolic medium, and we have again this behavior of the self-opposing, and in this case I show three examples of the propagation, but it depends on the number of the coherent states, and we can see different behavior depending on this varying this number. So we can construct other operators. Remember that the last ones allows to shift modes in this diagonal, but now we can construct other operators which allow us to shift different modes, but in the other diagonal. So we can define this. We can construct these new operators in terms again of the A and B capital letter operators in this way. So for that we define this set operators again as a combination of the A and B operators. So, and they satisfy the commutation relation this. So, to analyze the action of this operator onto the Hermite Gaussian beams, we define again new labels. In this case, is G and is mu. In this way, and we can find this satisfy the algebra of SU2. For that, we can construct other coherent states in this algebra SU2 using the parabolic approach, and we have which are defined in this way. So the coherent state is defined in this way. Again, I showed here this coherent state satisfy this inequality where these operators are defined in terms of the G plus and G minus. So we make a simulation of these coherent states, and here in this slide I show 3 examples of these coherent states, and we have again back to the bright levels in a rectangle arrangement, but this is particular because it's completely different from the others. And well, we obtain these graphicals using varying this parameter. So analyze again the propagation of these coherent states in a parabolic medium, and we have again this self-focusing behavior, and it is for different coherent states. Finally, I would like to conclude this talk mentioning the interesting things of this work, and we map the parabolic equation to describe the propagation phenomena of the light beam to the equation of the harmonic oscillator. So that allow us to construct to factorize these our Hermite Gaussian beams in terms of the ladder operators. So for that we can find that the algebras SU11 and SU2 generate all the spectrum of the Hermite Gaussian beams, and then to analyze the propagation of these beams we construct the coherent states using different approach depending on the algebra, and that's all.
How can you generalize this method to other systems? Have you in mind some other possible systems in which you can use this algebraic approach?
Yes, we have made the same analyze to Lugar Gaussian modes. So not only Hermite Gaussian modes, but we have made this for other system that is the Lugar Gaussian beams.
lectures, as far as I remember, in the talk by Producción, and also Contreras asked about the meaning of coherent states in the classical case. It is more or less your case because you are working with electromagnetic fields in the Maxwell context, and you have some algebraic approach to construct these coherent states, so that in which sense these states are coherent because they are already classical.
Yes, but we construct these coherent states using the definition of the coherent states. But it's true that our work is completely classical, but we use this tool, this quantum tool, to describe the propagation of the modes.
Kevin?
Well, it was basically the same question, but I have another one. So, anyway, so I was looking at your operators J. It looks like a Schwinger decomposition of angular momentum in quantum mechanics. So, in this context of classical optics, does it has any analog meaning, or does it have any physical meaning? This operator J.
Yes, but this.
Yeah, those ones.
Yes, we can express this like combination. Yes, but just now I can't remember the answer.
I can help you with that. You can map Hermite to Laguerre with superpositions of those, and Laguerre has an underlying symmetry and like angular momentum.
Oh yes.
And that's how.
Yes.
So does it have anything to do with angular momentum in classical optics? Like
In classical optics.
Okay, so it's the same meaning.
It's an analogy.
Thanks.
Any further question?
I have a question. Why didn't you take the job in octubre?
Okay. If there are no further questions,
So that was not a question,
That's not
that's an affirmation.
I don't know, but what's the question? Why? Why?
okay. So